In this video, we are going to quickly go over the concepts of spectrophotometry and how it uses Beer-Lambert's law in order to detect the concentration of solutes in a specific solution. Now, in a biomedical engineering setting, you would receive a lot of body fluid samples and you would have to assess the amount of specific solutes in those solutions, the body fluids. For example, you might want to detect the level of glucose in your blood, which would tell you a lot about what kind of diabetic condition the person is going through. So it is a very important law, and it would help us a lot in troubleshooting or maintaining such devices. Um, so it all starts with the test tube being filled with the body fluid. Let me just get my pen over here. Um, so this is the body fluid that fills up the test tube. Now, when we load this sample in the spectrophotometer, we irradiate it with a specific intensity of light, let's call it I1. Some of the intensity is absorbed, and the remaining intensity that comes out, let's call it I2. Now, depending on the concentration of the solute, the intensity of light that comes out of the sample is going to change. So you can imagine the more concentrated the solution is, less intensity of light is going to come out because more light is going to be absorbed by the particles in the solution. It's a very straightforward concept. So let's now introduce two more um, terms. Transmittance is nothing but what we saw in the earlier slide. So you had an intensity of light coming out and an intensity of light incident on it. You can always think about this as the light that made it out of the solution. And absorbance is exactly the opposite of transmittance, which is denoted by the negative log of transmittance. So this is the light that got trapped inside the test tube, inside the solution. And this gives us a measure of the concentration. How? That's given to us by Beer-Lambert's law, which you see on the slide right here. Beer-Lambert's law gives us an estimate of the absorption in terms of the concentration of the solute present in the solution. It depends on a few factors. One is the length of the light path through the solution. So this length right here, the distance that the light has to travel through the test tube, and the concentration of the solute. There is also a proportionality factor which is dependent on the type of solute that you are measuring. And when you have all of these parameters, absorption, the epsilon, the proportionality factor, which is determined by experimental results, and the length of the light path that it has to travel, that light has to travel through the test tube, you can calculate the concentration of the solute in the solution. When you are expecting output from these equipments, you would see something like this. So you have the wavelength on the x-axis and the absorption on the y-axis. So this is the light spectrum that you supplied to the test sample. And if the graph looks something like this, you would know that at a certain wavelength, the absorption was maximum. And this tells you a lot about what kind of solute it is and how much is the solute present in the solution. This setup would help you understand the concepts in electrolyte analyzers and spectrophotometers that would be covered in the chapters that are further to come.